Okay, should we keep going? So I've got one more example I want to do. So I could go on to do more theory stuff, but I think probably it's good to do an example. So this is one example of using the one-step look-ahead rule. Okay, it's not too hard, so we'll do that, and then we'll see where we get to, and that'll probably be a good point to stop for the day. So here's a kind of like nice kind of exam question, style question on one-step look-ahead rule. So I had one a bit similar to this last year on like you've got an investment and there's some interest rate associated with it, and there's a stopping set and things like this. Okay, so you're looking for a parking space in the street. Okay, so you've got a car. It's a big long street. There's parking spaces along the street, and it's a one-way street, so you can't turn back. Okay. And on that street, each space is free with probability P, which is equal to 1 minus Q. Okay? Right, so you can drive along the street, space is free, you can either park or not. Okay? Okay, so each space you have to decide to stop or not. Okay? And you're trying to get to the destination, which is at the end of the street. Okay? So let's suppose that your position is given by S, where S is the number of spaces from your destination. Okay? Now, the cost of stopping is S, is your distance from the end of the street where you want to end up. Okay? So if you stop straight away, you have to walk the whole length of the street. Okay? If you stop at the end of the street, or try to stop at the end of the street, that's good, but it might be that the very last space that you turn up to at the end of the street isn't taken, in which case you incur some big cost D, because you've got to drive around all over again. You're going to get back all the way back to the beginning of the street or whatever. Okay? So the question here is to find an optimal policy for parking. Okay? So you've got to decide when you're going to decide to stop. Okay? In fact, on a kind of slightly tangential note, so Paul Johnson, who does your computational finance course, did lots of dynamic programming things for Manchester airport car parks. So they kind of vary the prices and try to control whether people park there and things like this, using Markov decision processes for deciding how they should price the car parking spaces. So, you know, car parking and Markov decision processes aren't actually, it seems like a fun example, but they're actually very connected, at least in Manchester they are anyway, at the car park at Manchester International Airport. Okay, anyway. So let's answer this question. Okay. So I'm going to let one component of the state. The state isn't just whether the space you're next to is free or not, but the state is also the position of the car. I'm going to let x of s be the indicator function that space x is free. Okay? All right, and it's not quite so hard work to write down the Bellman equation for this guy as it was for the secretary problem. Okay? So let's suppose we're looking for the cost associated with being in position S, okay, and the space, let's say in this case, is free, okay? So we've got two choices, I either stop or I continue, okay? Okay, so if I stop and park the car, what's the cost? So I'm trying to minimize the cost. I think someone said it. So the cost of me stopping is what? So, say again? S, yeah? Okay, and that's it, okay? All right, and there's no continuation cost, okay? So what's the expected, so I'm going to drive from position S to position S minus 1, the next place, okay? So we have to look at what the expected cost of that is, okay? So two things can happen. I drive one space further, and either the space is free or it isn't free, okay? So with probability P, the space is free, okay? And then I get the cost of, S minus 1 spaces to go, okay? And I arrive at a free space. Or, okay, with probability Q, equal to 1 minus P, I get the cost of being S minus 1 spaces to go, and there's a space that's taken. Okay? All right, so that's the Bellman equation for the state where the space is free. Okay, remember we had it with the machine being broken and not broken, so it's very similar to the machine being broken and not broken problem. And we're to look at the case where the space isn't free, okay? So if the space isn't free, I can't stop, okay? So the action that I can take is only to go to the next space, okay? All right. So then I just drive to the next one, and the cost is exactly as it is here. With probability P, that next state is space is free, and with probability Q, that next state is not free. Okay? Okay. Okay. So we're going to define here the kind of one-step look-ahead set. So the rule here isn't really like I wait for a space and I look at it and I stop, but really actually if notice from here, the rule I'm applying is actually I just kind of drive to the next available space and then I have to make a decision. Okay? So let's consider the following stopping set. S, where if I'm in a position S, okay, so S car parking spaces away from the end of the street, okay, and let's assume that that space is free, okay, then I want to look at the stopping set for this guy, all right, so either I stop at that point and incur a cost of S, or I continue to the next space and then take the next available space. That would be the interpretation of the one-step look-ahead rule in this case. Okay? So I'm going to let K of S minus 1, I'm going to introduce a little bit of notation, okay, where K of S minus 1 is the cost of taking the next available space from position S minus 1 onwards. Okay? So the interpretation of the stopping set here is I either stop now or I continue and take the next opportunity to stop. Okay? It's a little bit different to the way I defined it earlier, but it's kind of the same. Basically, the logic is exactly the same. Okay? So now we've got a job to do. We need to calculate what this ks is. Okay, so I haven't really defined what ks minus 1 is here. Okay, if I was to ask you this question in an exam, I'd probably say, write the stopping set in this form k of s and try and find what k of s is. Okay, so luckily we can express what this is. Okay, so if I'm looking for the cost of taking the next available space, with probability p, the next space is available, okay? And then I incur a cost of s, okay? And with probability q, the space isn't available, okay? In which case, I get a cost of ks minus 1, okay? Okay? And I also have the part that k of 0, okay, the cost of taking the next available space from 0 onwards, okay, is either 0 with probability p, because the very last space is free, or with probability q, there's no spaces available left, and I have to incur that big cost of d. Okay? All right. So this is a specific type of recursion, and it has a kind of a specific form. Okay, so again, I wouldn't like ask you to know the kind of how to solve these kind of. Again, it's a difference equation. Okay. And it has a form like this. Okay, it's a bit similar to having a differential equation of the form something like that. Yeah, it's a bit similar. Okay, so if you solve differential equations of this form, you're going to find solutions a bit similar to this kind of thing. Okay. Okay. Anyway, so you can check where c is some constant here, that c is equal to d over 1 plus p. Okay, so basically you've got a recursion that's satisfied by these costs. Okay, you can check that these kind of solutions are solutions of this recursion, and you can check from the initial condition that this is the correct initial condition. Okay, so again, like I say, this isn't a course on like knowing how to solve difference equations, so that's just kind of given information. Okay, so substitute this into the stopping set S, we'll find that actually we end up with the condition. So this S will cancel with this S, and we'll be left with the following condition, that dp plus 1 q to the S has to be bigger than 1. Okay, that will be the condition I get from rearranging this expression. Okay. Okay, so basically, I write down the Bellman equation, I characterize the stopping set, I work a little bit to get the stopping set into a nice form, okay, and remember that the other thing that we needed to check was whether the stopping set was closed, okay? So why is this stopping set closed? Why once I reach a state S, okay, where this is satisfied, can I never enter it? Sorry, can I never leave that set? Ooh, and I think I've got this inequality. Is this inequality the right way around? Check this. Ah, yes. So notice that if I started, for example, with 100 here, okay, then this would probably be less than 1, okay? And then I go to like s equals 99, and this number's a little bit bigger, okay? And if I go to s equals 50, it's going to be dp plus 1 to the q to the power of 50, which is going to be a bit bigger, okay? If I eventually go all the way to s equals, let's say 0 here, I'd have dp plus 1, which is definitely bigger than 1, okay? So notice as I let the numbers s get smaller and smaller and smaller, this number here is getting bigger and bigger and bigger, okay? So once it passes the threshold of being bigger than 1, you can never go back down again, okay? So essentially this, so here, as s gets smaller, this function increases, i.e. this set is closed. Because once you're bigger than 1, you're going to be bigger than 1 forever. Okay? So, the optimal policy is to take the next available space once the condition dp plus 1 is met. Okay. Okay. So that's the basic structure of how to apply one of these optimal stopping one-step look-ahead problem questions. Okay. Write down the dynamic program, write down the stopping set. You have to work a little bit to characterize the stopping set in a nice form, and then it usually goes like this. It says that, you know, something's increasing or something's decreasing. So that means that the condition for the stopping set is met, and you can't ever exit the stopping set once you're in there. Okay? And so then you can say that the one-step look-ahead rule in that case is optimal. So I just write that. So I should really say here, so one step look-ahead rule is optimal. So the one-step look-ahead rule is optimal. Can't spell today. So the optimal policy is to make the next available space after this condition is satisfied. Okay. So that's how you kind of trade off between the cost of having to return all the way back round compared to the kind of improvements you get by getting increasingly closer to your final destination. Okay. So next time you're parking at the beach or whatever, you can keep that in mind. Okay. Every time I go to the beach when I'm in Manchester, I remember this question. Good. Okay. Right, we'll do a little bit more optimal stopping next time, and then probably we'll start to work towards kind of continuous time theory. So we'll be working on our Taylor expansions and all the rest of it next time. Okay, so, okay, good. Thanks for coming.